All right, now let's move on to the quotient rule. So looking at the quotient rule, again, intuitively I would think, oh, this just means to take the derivative of the top function divided by the derivative of the numerator. That's what I would think to do. But let's see if that's the case. So if f of x equals x to the 7th and g of x equals x cubed, does the derivative of f of x divided by g of x equal the derivative of f of x divided by the derivative of g of x? I don't know, let's try. So d over dx is, so x to the 7th over x cubed. Okay, properties of exponents, that's going to simplify to x to the 4th power. And now I can actually take the derivative, so that gives me 4x cubed. All right, when I look at doing it the other way, that would be d over dx, oops, let's do this in a different color, d over dx of f of x over d over dx of g of x. So that would give me 7x to the 6th in the numerator over 3x squared in that denominator, which gives me 7/3 x to the 4th. These are not the same. So we cannot just take the derivative of the numerator divided by the derivative of the denominator. So the formula for the difference quotient, or the quotient rule, excuse me, the formula for the quotient rule is as follows. It is the function in the denominator times d over dx of f of x minus f of x times d over dx of g of x all over g of x squared. Again, if you want to write that with less letters, it would be g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. Let's go through and check this with this problem now. So if I were to do this now, all right, so if I were to find the derivative of x to the 7th over x cubed the long way. So this is obviously the shorter way to do it, is simplify. If you always can simplify what's in there and not have to use quotient rules or product rules, obviously do that. But let's just say we didn't see that we could do that, and let's apply this formula. So our g of x is x cubed, our f of x is x to the 7th. So it is g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. So that's going to give me x cubed times 7x to the 6th power minus x to the 7th times 3x squared all over x to the 6th. So that becomes 7x to the 9th minus 3x to the 9th all over x to the 6th power. So that gives me 4x to the 9th power over x to the 6th power, which becomes 4x cubed, which is exactly what I needed it to be. So again, you can see this took a lot longer than what I did here. So what I always recommend students do is when you're dividing two functions or even multiplying and finding the derivative, first see if you can actually simplify the quotient or product and then apply derivative formulas. And if you can't, then go through and do these quotient rules and product rules. Let's look at an example using the quotient rule. Differentiate y equals e to the x over x. Okay, so I have two functions getting divided by each other, e to the x and x. I can differentiate e to the x, and I can differentiate x. I can't differentiate this quotient, though, without using that quotient rule. All right, so derivative of y with respect to x is going to equal, so using that quotient rule, so it is the derivative, so the second function, it is the denominator, so g of x, so there's our g, there's our f. So g of x, which is x, times the derivative of f, minus f times the derivative of g, all over g squared. So that's going to give me x, e to the x, minus e to the x times the derivative of x is 1, So it's just going to be e to the x times 1, which is e to the x, all over x squared. All right, let's look at another example using the quotient rule. Differentiate g of r if g of r equals r minus 1 over r squared plus 3. So I can see here I'm going to end up using that quotient rule. I can't simplify this any further. Okay, so we will get g prime of r equals, so the bottom function times the derivative of the top. And in this case, I'm doing it with respect to r because r is that input value. So make sure you're writing d over dr instead of d over dx. And then minus that top function, r minus 1 times the derivative of the bottom, r squared plus 3. And then that's all over that denominator squared. Okay, so this is going to give us r squared plus 3 times, so the derivative of r minus 1, so that's going to be the derivative of r, which is 1, minus the derivative of 1, which is 0, so that's just going to give me 1, minus r minus 1 times the derivative of, so the derivative of r squared is going to be 2r, and the derivative of 3 is 0, so 2r plus 0 is just 2r, and then that's all over r squared plus 3 squared. Just simplify this out to see if there's anything that will cancel. So I'm going to first distribute this through. I'm going to keep that minus sign in front first. So I'm going to get 2r squared minus r all over r squared plus 3 quantity squared. So that gives us r squared plus 3 minus 2r squared plus r all over r squared plus 3 quantity squared. So that's going to leave me with negative r squared plus r plus 3 all over r squared plus 3 squared. There's nothing else I can do from there. Okay, let's look at this one. So this one, oh my gosh, it's a little more complicated, right? We have products, we have quotients, we have so much stuff. We have e to the x's. So let's go slowly. So the first thing I see is that I have two things getting divided by each other. So we're going to start with the quotient rule. Okay, so we'll call this our numerator function, so our top function, and we'll have this one be our bottom function. Okay, so let's first set it up that way. So using that quotient rule, so the derivative of the function z with respect to x, because x is our function here. Okay, so that's going to be the denominator, so the bottom function times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Okay, so let's just work this through. So I get x to the 4th minus 1. Okay, so to figure out this, that's the derivative of two functions getting multiplied together. So I'm going to have to use the product rule here. Okay, so to differentiate those, that's going to be the first function times the derivative of the second plus the second times the derivative of the first. Okay, I just did it in that other color just so you could kind of see where that's coming from. I'll actually just keep the parentheses in purple. So in that case, this is where I had to go through and use that product rule because I can't actually figure out what the derivative of x cubed e to the x is without using that product rule. Okay, and then that's going to be over, or subtract e cubed, or x cubed, e to the x times, so the derivative of x to the 4th is going to be 4x cubed minus the derivative of 1 is just 0 because that's a constant. And then that ugliness is all over x to the 4th minus 1 quantity squared. Okay, so then that's going to become x to the 4th minus 1, and that entire quantity, so don't forget your parentheses, So that's getting multiplied by x cubed. The derivative of e to the x is e to the x, plus e to the x. The derivative of x cubed is 3x squared. So now I found that derivative. And then when I simplify this second term out, I'm going to get 4x to the 6th power e to the x all over x to the 4th minus 1 quantity squared. Okay, now if you wanted to, you could kind of go a little bit further. It doesn't simplify anymore, but if we wanted to, we could kind of make it look a little cleaner. I can pull an e to the x out of both of those terms and an x squared out of both of those terms. So if I factor that out, an e to the x and an x squared, I'd be left with an x plus 3. And then I still have this minus 4x to the 6th e to the x all over x to the 4th minus 1 squared. And this just ends up getting pretty yucky when you go all the way through, so we're going to leave it right here. Let's look at an example of an application where we have to use the quotient rule. Let the function v of t equal 6 times the cube root of t all over the quantity 4t plus 1 be the volume in centimeters cubed of a balloon at time t in seconds. Find v of 8 and v prime of 8 and interpret both in the context of the balloon with units. Okay, so v of 8, all that means is you're just substituting the 8 in for t and v. So that's going to be 6 times the cube root of 8 all over 4 times 8 plus 1. So the cube root of 8 is 2 all over 32 plus 1. So I end up getting 12 over 33. And then our units are going to be centimeters cubed, because v spits out that volume in terms of centimeters cubed. So what does this mean? So this means at 8 seconds, the volume of the balloon was 12 over 33 centimeters cubed, or approximately, if we wanted to approximate it, you could put that in a calculator and you'd get it's about 0.34 centimeters cubed. Okay, so if I wanted to figure out the first derivative at 8, let's first find that first derivative formula. So v prime of t is going to be, so I'm going to have to use that quotient rule here. Okay, so it's going to be the denominator times the derivative of the numerator plus the numerator times the derivative of that denominator all over that denominator squared. So that's going to give me 4t plus 1 times 6t to the negative 2/3. You find this derivative, plus 6 cube root of t times 4. The derivative of this is 4, all over 4t plus 1 squared. Now this is really ugly, and we definitely, if we were trying to find an answer for what is v of prime of t, we would want to keep on going to simplify this. But I'm not looking for that. I'm looking for what is v prime of 8. So now that I actually have the formula for this, even though it's really ugly and not as simplified as it should be, I can actually just plug this in. So v prime of 8 is going to be 4 times 8 plus 1 times 6 times 8 to the negative 2/3 plus 6 times the cube root of 8. Actually, and this should all be a minus, shouldn't it be? So quotient rule is subtracting. Okay, so minus 6 times the cube root of 8 times 4, all over 4 times 8 plus 1 squared. Ooh, that is ugly, ugly, ugly. Okay, so that's going to end up giving us, if you throw that into a calculator, you're going to end up getting in the numerator negative 6, it'll be negative 31.5. And then in the denominator, we'll get 1,089, which is about negative 0.0289. All right, let's figure out our units. So our units are going to be, so this is the derivative of the original formula, so change in y, so cm cubed is those units, over the change in x, which is t in this case, which is seconds. So centimeters cubed per second. So what this means, if I was interpreting this, is I would say that after 8 seconds, or at 8 seconds, you could also say, the balloon, so this negative means we're decreasing, so it's a decreasing rate, so is decreasing or deflating, since we're talking about a balloon, at a rate of 0.0289 centimeters cubed per second. So I don't say decreasing at a rate of negative, because the decreasing takes care of this negative piece. So it's decreasing, and the rate that it's going down is 0.0289 centimeters cubed per second.